someone Clausel.
Okay.
Working at the University of Lorraine in France. She's well known both in the area of math and stats and machine learning.
With friends.
In each month. And so now I give you the floor. Thank you.
Okay, thank you very much, Florence. So, and thank you for the invitation. I'm very glad to discover Cambridge and the Isaac Newton Institute. What I will present you, it is some work that has been done in collaboration with Konstantin Izevich and one of my PhD students, with Raphaël Mignot. And it is about multivariate time series. And we explored what is called the signature method. The signature method, which is somehow an analogous of the moment method for time series. So first I will give you some motivation about multivariate time series, but I think everyone is motivated. So, okay, I will go fast. Thereafter, I will explain what are the signature method, and I will give some example of application. Probably I will explain this question about barycenter. I don't know if I will be able to talk about PGA and causality. Okay, so let's go. So everyone is motivated about multivariate time series because it is ubiquitous in all areas of sciences. So some example, finance, neurosciences, earth science, and everyone wants to discover and to study this topic because it is an important topic. And the point is that if we study multivariate time series, we have to take into account two kinds of dependencies. We have to take into account temporal dependencies within each time series and spatial dependencies between components of the multivariate time series. And the claim of the talk is that the signature method is a nice way to do so. Okay, so just two examples, but really classical examples. So financial time series. So for example, if you are considering financial time series, you may want to cluster these financial time series. You may want to study them. So here, for example, here you have the date of 2006 and 2007, which is a crisis that you can see on this financial time series, and you have two different behaviors with respect to this crisis. Okay, and you have also another nice application is neuroscience. It is known that if you are considering the brain connectivity, there are several areas in the brain. Some are related, for example, to language, to vision, to anything, and some people are studying what is the connectivity which is within the different area of the brain. Okay, so people are studying that. Okay, and the point is when you study this kind of problem, when you tackle these problems, a lot of people are considering pairwise interaction because it is a nice way to do so. And there, for example, here, to tackle this problem of connectivity maps, people are studying, for example, correlation maps. Or here also people may study correlation within the time series, okay, precision matrices and so on. And it is a nice way to do so, but what we want to do, we want to go further and to study interaction, not only pairwise interaction, but considering possibly interaction between 3 time series, 4 time series. And to do so, we need to extend this analogous of correlation to considering high order and non-symmetric dependencies. And a tool that we propose to use is iterated integral signature. Okay, and somehow to understand what it is, you have to think to this method as a moments method. It is, you have somehow the same properties. Okay. So first, we shall speak about these features, okay? Thereafter, we shall speak about possible tasks, and if we have time, maybe we will speak about other tasks as PGA, causality, and so on. Okay, so first, these features are very simple features. So you have a multivariate time series, okay? And what you are considering, basically, it is integrals, okay, of this time series. So at order 1, in fact, you are considering the average, the difference, the increment of this time series. So here you have signature of order 1, okay, it gives you something which is first order information, which may be interesting. The second order encodes somehow the causality in a very loose way. So I will explain why with a small example and a small picture. So if you are at order 2, you define recursively these integral features. So as follow. So first you are considering your features at previous order, and then you integrate it against your new component. Okay, and the point is there are several things to remark. So it is really an analogous of cumulants. So at order 1 you have a vector, which is an analogous of the mean. At order 2 you have a matrix, which is not a correlation matrix, but which is a matrix encoding something about the multivariate time series. At order 3 you have tensors, and at order 4 you have tensors, right? So the point is that it is a complex object, and you may think to this complex object having several points of view. You may think about moments, the extension of cumulants or moments. You may think also about this signature as a Taylor expansion, which is another point of view. So in fact, the more the higher the order you consider, the higher you have some information about your multivariate time series, and it is like moments or like cumulants, in fact. So just to give you an example, I will detail the signature of order 2, just to give you an example, and so that you understand what it can encode. Okay, so here, very important point, you have that. So have in mind that as order increases, it could be really a burden to store the signature. So for example, if you are considering order 4 or order 5, 6, even for a 10-component multivariate time series, you will have a lot of coefficients to store. So have this in mind, okay? And in the future, maybe we can develop strategies compressing this tensor, considering, for example, CP decomposition or other kind of decomposition to store this coefficient. So it is really a true problem, okay? So it is really complicated to store the signature, but on the opposite, we have nice properties from the signature. Have in mind that it is integrals, basically. So you recover all properties of integrals. So mainly you have a shell relationship, okay, because it's an integral. So you can consider slices of signature, okay, because it is integral. So it is not so difficult to compute because it is integrals. And then since you have these properties, these slices properties, what you can do, you can compute the signature. You can consider, for example, a piecewise linear path, and thereafter you compute your signature on each part, and thereafter you can compute the whole signature. Okay, so it is not so difficult to compute. If you want to compute it in an efficient way, it is possible, and some researcher has done that very. Yeah.
This is element-wise.
No, it is really, no, it is a complicated product. In fact, it is the signature. You can consider it as a formal power series, and here it is a product between formal series. In fact, you have to consider the signature as polynomial. In fact, and then you have rules to compute the product of signature. So I can show you, for example, here I give some example, blah, blah, blah. Okay, in the example, just to show you. So for example, you have rules to compute the product of signature, and you have rules also to concatenate paths and to see the impact of the signature. You have algebraic rules, in fact, which can be recovered because so since you have integrals, okay. So for example, when you multiply two signatures, it is somehow a Fubini theorem. So you have properties as this that I showed you. And if you concatenate paths, since the signature it is also an integral, you can divide you can divide each integral, and then you have algebraic properties showing the link between the whole integral, okay, and the integral on each path. And you have formula, you have explicit formula which are quite ugly, but you have explicit formula, and it is coming from the fact that you can do slice for integrals and that you can do Fubini formula for integrals.
In the definition of the signature for
yeah.
different order?
Yeah.
For what?
Yeah. Thanks.
Okay, so at the beginning, it is just an increment.
But it's indexed, so A and T are fixed or they are varied?
Ah, yeah, sorry. Yes, A and T are fixed. Yeah, A and T are fixed because here, okay, when you integrate, okay, it is somehow you are integrating. So is there yeah.
Yeah, that is good.
I can write it.
There is short there.
Ah, okay. I can write it okay. Here. Oops. Alors, just to show you, it is something which is so. For example, so I have x1, xp, my multivariate time series. Okay. So thereafter, I define, for example, okay. So imagine that, for example, if you are smooth, okay. So here you have. So this definition can be extended to loose path, but if you are smooth, you have something like that. Okay. And thereafter, okay, if you want to define, okay, so I just put the formula so I can see it. Okay, up, so that I can see it. Okay.
Yeah. The derivative is in terms of the spectrum or in terms of approximating the derivative?
Alors, there are two things. Here it is a theoretical definition.
Yes.
And thereafter, to calculate it in a practical practical situation, what we do a linear approximation, a piecewise linear approximation of the path. And then if we do a piecewise linear approximation of the path, it is not so difficult to calculate it in an explicit way. But there is an approximation because in practice, you have time series. In practice, most of the time, you don't have a continuous path, you have a time series. So what you are doing in practice, so here, what you are doing in practice, you have your time series, and you interpolate, and you calculate after that.
Taking the instantaneous derivative at the first order.
At the first order, yes, it is here, it is a derivative. Yeah, at the first order, it is a derivative. Is it okay? Okay.
So, for example, if it's coming from differential equation like x dot is equal to minus x.
Yes,
So
in this case, there are, for example, if it comes from controlled differential equation, you can compute, for example, if it comes something like that, if it comes something, you can compute the signature. You can, there is another way to compute it.
Okay.
You can use your equation to compute your signature. And in fact, it is coming from the root path theory. And at the very beginning, what has been considered, it is a continuous solution, path satisfying, for example, ODE or CDE.
So there you would compute the integral of f, or so it would be the average of f, or so the first order.
No, at first order, in fact, you are, yeah, you are here. What you are computing, okay, yeah. I am not precise. You have x, which is your time series, or your path, and here what you are computing your integral.
Yeah, but then if we do it this way, it will be the average of f. If you replace dy by f ds, then this would be the average of f, or no?
Yes, it would be the average of f. Oh. But what you can use, you can, for example, you can try to use, for example, the Taylor expansion of f, and try to use recursively the expansion of. Yeah, you can try to use in a recursive way this equation to compute the signature. Okay.
Okay.
So the point is that when we say we average f, okay, we don't. Yes, we use, but in a very basic way, the relationship. Here, what we try to do, we try to compute the signature from the data. So here we give a definition, which coming from the data, and we try to consider the time series. And from the time series, we want to define these features, which are integrals. So it is another perspective. Here, you may have a model. You are not considering at first the data. You have a model, and you try to derive some nice theoretical properties of the signature. And our perspective is different. We have data, and we try to have features, encoding the relationship between components of the time series.
Marianne, can you show again the first slide for higher order?
Yeah, for higher order, yeah.
I'm confused with the index.
For higher order, so for first order, it is, I think it is clear. So here, for higher order, what we have, okay. If we have this, okay, we have this integral, okay, okay, and thereafter here we have the signature of order 1. So here we have integral from 0 to S2, okay, which is it is S1, okay. It is iterated integrals.
Well, what's the upper limit on that? Oh, S2. In the integral, I thought we need to find the first order.
Yeah, here you have your first order. Here you have S. You have your first order, but you have your first order not from 0 to 1, but from 0 to S2.
the antiquating one.
So then it's not fixed at the end of the day.
Exactly, it's not fixed. In fact, you are integrating. On a domain like that, and it is a reason why it is non-symmetric. In fact, somehow you try to understand if there is some delay between X, this first component, and this second one. It is a reason why it is encoding somehow causality. In fact, in this iterated integral, so I show you also order 3. In this iterated integrals, what you try to understand, it is how you encode somehow the delay. So you have this. So the important point is that it is non-symmetric. And you have okay. So you have this, in fact. And here you are looking somehow how, in fact, if you are purely aligned between first component, second component, and third component, it means that there is no delay, in fact. So it is not exactly a cross-correlation. It is a non-symmetric cross-correlation. It means here, what you are trying to see, it is the lag between the time series. And it is the reason why it is widely used in financial time series, because people are interested in lags, they are interested in causality. And to see, for example, there is a lot of paper about this lead lag approximation. For example, you may assume that gold is the main financial asset, leading, influencing everything. Yeah, exactly. For example, yes, exactly. So, for example, what we try, a question could be: is gold influencing Bitcoin, for example, or dollars, or anything you want? And then you try to see that with iterated integrals, because basically, if there is no delay between the effect, here you will have the maximum when you have something like that. So you try to capture pairwise interaction and beyond, because, well, and it is interesting, the interesting features of the signature. And it is really done there, and the point is that you are not integrating in a symmetric domain. Yes, the domain is, there is truly an asymmetry inside the signature. So it is truly asymmetric, and it is a reason why it could be also interesting, because, for example, in the talks that we saw yesterday, in fact, there was this influence, for example, of pollutants from one city to another one. So there is truly something which is asymmetric that we want to capture in this case. So there is a lot of cases where there are true asymmetries. And we want to see that in a feature, which is basically a large sequence.
So in classical time series, with kind of box style approaches, you have the differences, right? So you're playing around. If you think discrete, you're playing with
exactly.
Components and
exactly. And there are a lot of works about the way to discretize this signature. And it is like a discretizing scheme. Discretizing scheme, you have several versions, you have several ways, several properties, and it is exactly the same question, basically. And there is a linear way to do. There is a linear way which is to say, okay, I have a continuous space. I am considering the piece linear. Okay, so there are several. Yes. Okay, I will just. So you have several ways to do so. So in fact, you have your path, and you have several ways to discretize your path. So there is the first way, which is Okay, I am linear. I interpolate in a linear manner, and you have, okay, it is the same idea. Okay, if you remember your basic undergrad for integral, if you want to calculate integral, you have several ways to do so. And it is exactly the same idea. As soon as you have in mind that signature is with integrals, you catch everything. And the point is that it is asymmetric, and we are going to explore, to think about this, because it is an interesting feature of the signature method.
So maybe just a question, but what's just like when you say you catch everything?
No,
what does it mean? So if you have a chaotic system like a Lorentz.
No. I'm very sorry. Yes, it was just to say that it is really an important feature of the signature, and a lot of properties of the signatures are coming from the fact it is an integral. But I apologize. They are very, very complex systems like ODE, SDE, and there is a lot of work to do to understand how works the signature.
Okay.
So I apologize. It was just a short sentence to try to summarize an important features on my point of view.
I just thought that there was like a proofs where you say if you have a chaotic dynamical system, you can get everything through it.
No. I'm very sorry about that. No, sorry for the confusion. No, it's not that. It is just that since it is an integral, we recover very nice properties from the signature. So, for example, first nice property is this one. Okay, we can divide, and it is exactly here. If you divide, imagine that your integral, you divide it. Okay, you can divide, you can, and then you have, imagine that here you have your signature from 0 to 1/2, and from 1/2 to 1, and thereafter you have properties. Okay, so it is just to say that, okay, and to prove this property, which is not trivial, you use inside there is a key property of the integral, which is that we can split integrals. Okay, and it is so in fact we have two main properties. We can split integrals, and then we can approximate in a Roos way. We can approximate any smooth path using piecewise linear function, or polynomial, or spline, or whatever you want. Linear are quite convenient to compute the signature, because after that you will have a recursive formula, and it is nice. Okay, but it is not the only way to do so. Okay, it is just one way which is convenient.
Yeah, I'll have more questions later.
Yeah, please go.
Now for me, for example, if I give you the Bernoulli map or like logistic map, xk plus 1 is equal to rxk times 1 minus xk.
Yeah.
So what can you tell me? Because this is known to be like a very simple toy model in chaotic system.
Yeah.
It's very rich because it depends on R. So what can you tell me based on your signature? Can you, for example, identify the different regimes of the logistic map based on R, and then you compute, or I don't know what can you tell me?
Maybe an idea to identify the different regime would be to compute the signature on slices and try to find the change point.
As a function of R, or
yeah, as a function of t, because you have a
for me, like the main parameter is R. So
okay. Yeah, depending on R, you may try to find different regime. For example, you have different population of signature, and maybe you can try to see if depending on this R parameter there is a change in the distribution.
Okay.
It could be an idea. I don't claim at all that it is easy.
Yeah, we can discuss later.
Yeah, but at first it would be my first idea.
Okay.
To say, and maybe to have, for example, a change point detection based, I don't know, on the Wasserstein distance, for example. Okay. But like that, it is easy to say, okay, that's easy, let's do it. But Maybe in practice it is not so simple.
Yeah.
But it could be a tool to, for example, to test, to have change point detection. Maybe we can try hypothesis testing. Okay. Okay. So now I will try to give you some ideas about what could be the interpretation of the signature method. So I will focus on order 2, and on order 2, a very important point. So you have this formula, okay? So this formula, have in mind that it is just a Fubini formula. So here you have an integral of order 1, here you have an integral of order 1, and here you have integrals of order 2. And it is, okay, and it is not so difficult. In fact, you have integral of order 1, okay? You have integral of order 1 on a triangle. You have integral of order 1 on the opposite triangle. And then, so you have a Fubini-like formula here. Okay, so this kind of formula, it is a Fubini-like formula. Okay? And what it means that the signature of order 2 is redundant. Inside the signature of order 2 is included something of the first order. Okay? Because of this relationship, which is the Fubini formula. Okay? So in fact, if you consider the symmetric part of the signature, there is no information with respect to order 1. But all the information is included in the anti-symmetry, in this Q-symmetric part, okay, which can be defined like that. And we may want to understand on a small example what it could encode, and just I will show you. So here I'm considering several paths, okay, and here you have this idea of delay, okay. So if you remember, I told you that somehow we are trying to understand what is the delay between two components. Okay? So here we are considering the case without any delay. Okay? The two components are working together. They are doing the same thing at the same time. Okay? Here we have some delay. Okay? The first component is increasing and the second one is doing nothing. And here we have the opposite case. The second component is growing, is increasing, and here we are doing nothing.
What's P?
P is a path, in fact.
Component 1 is I'm sorry.
Yeah, component-wise.
One of the two.
Alors, component-wise, just to show you. So, just P3. I just explain you what is P1 and P3. So P3, it is you have x1 equals t, x2 equals t. Okay? So t. Okay. And P2, P1, the first component is increasing. Okay? Okay, and the second one is 0. And here, thereafter, x1 equals 1 from 1/2 to 1, and x2 equals 2t minus 1. Okay, so we are increasing here. We are first increasing the first component, okay?
Yeah. Just to understand, you give here an example.
Yeah.
It's an example.
Yeah.
And you choose x1 equal to t.
Yeah.
And the x2 is
0.
Is constant, okay. And then you begin to compute your.
Yeah, exactly. And in each case, I compute this Q-symmetric part of the signature. And here is a result.
Okay, and A
is an area. Is an area because here we have this Q-symmetric. In the skew symmetric, I define it is not exactly the signature. So here, what we remark that from if we go from order 1 to order 2, okay, the only gain of information is in the skew symmetric part of the signature. The signature of order 2 is a matrix.
Yeah.
It's a matrix. And this matrix, there is a symmetric part and the skew symmetric part. And in the symmetric part, basically, you have nothing. Because basically, it is the product of the order 1. So you have nothing. So what is interesting is not the symmetric part, but the anti-symmetric part, the skew symmetric part. And we focus on it. And we try to have an intuition about that. Here you have order 1, order 2, and here you have this matrix which is defined like that,
yeah.
And you have symmetric part,
yeah.
Skew symmetric. So you have a matrix, and you calculate basically your symmetric part and skew symmetric part.
Okay. And now you take your example.
I take an example.
Show in the picture the different values.
Exactly, and the idea is to say, okay, the message is that we want to capture the delay between these two components. And since we want to capture the delay between these two components, we consider 3 extreme cases. First extreme case, we have the first component who increases, the second is doing nothing, and the after. Okay, so we have a delay.
Yeah.
Okay, the delay is 1/2. Okay, here we have no delay between the components. Okay, and we try to understand what happens.
Okay.
It is an example. It is not a proof at all. And the proof would be false, absolutely false.
Okay, so now I think we can.
And it is just to gain intuition, to have intuition. It is not a proof at all.
Okay.
And here, what we have, what is our intuition on this example, okay, which is only an example. The intuition is that if we have some delay, it can be captured in the skew symmetric part of the signature. And it is the intuition. So the intuition is, and it has been used in some paper to test the causality as a proxy. The intuition is if there is no delay between the two components, the skew symmetric part will be 0. If there is a positive delay, that is, if the first component is increasing before the second one, the skew symmetric part is positive, and third case, the skew symmetric part is negative. So it is the intuition. And this intuition is not true. I think the situation is much more complicated because we need all the moments, in fact, of the time series to understand what happens. Because, for example, if you want to study the pattern in a causal graph, you have many patterns. And you have only simple patterns. Okay? So it is just an intuition, but the point is that some people have used this signature of order 2 for causal discovery as a proxy. Because the signature of order 2 is something easy to compute. It is an integral, it is easy to compute. You can perform a non-parametric test, and some people have done this. Okay? So it could be interpreted in a very loose way as a proxy for causality, which is not true, because after that, some people of Oxford, sorry for the name, some people, notably a former student of Terry Lyons, proves that the right way is to use kernels. Yes, the right way is always kernels. Yeah, so you can kernelize the signature. And if you kernelize the signature, you can have independence test or conditional independence test using kernels. So you extend kernel conditional independence tests, you can extend them using the signature. So it is not true, but we have some intuition like that. So there is now a second question. In fact, we have features. Okay, so we have time series. Using these features, we go to another space, which is a signature space. And we may want to invert the signature to say, okay, I have the signature. So maybe if I know the whole signature, I can try to find the signal. Okay? The problem is that it is not true because the uniqueness property of the signature is up to some what we can call loops. So if you have loops, the signature doesn't see these loops. Okay? Because basically, if you for example, if you do something like that, and thereafter you come back, you have an integral which is 0. And you cannot see that. So you are not unique.
It's quite general, so it's for general path.
Yeah.
And when it is really time series, as we have daily observed time series, then we have not this kind of.
Yeah, true, exactly. Yeah.
Specific case.
Yeah, exactly. But anyway, the problem is ill-posed.
Okay. Yeah.
Anyway, from the numerical point of view, even if we are, I agree, I fully agree, this pathological case, it never the cause. But in practice, the problem is ill-posed anyway, and it is not simple to inverse the signature. So in my lab, we have a colleague working in this inversion problem of the signature with people of Tübingen, and they try to do something like that, penalizing the problem, okay, imposing a structure on the data. But in itself, the problem is ill-posed. Okay, so a lot of people also have studied this signature method. So the team of Terry Lyons worked a lot on this signature for machine learning. And a former student, thanks to Arturo, discovered that a former student of Telecom Paris is also working on the signature method. So the signature method is everywhere. And he wrote a nice paper about anomaly detection with kernel. Voilà, kernel. So kernel, signatures on kernel are everywhere. So you can read this nice paper about anomaly detection and isolation forests using also the signature method. So what I am trying now to talk about is the fact that in ML, I will send you the paper.
The isolation,
Yeah.
we designed, I mean, we designed the paper. I mean, well.
Yeah, true. Okay, yeah.
I mean, it's not as.
Yeah, true. Okay, but it was a nice paper, and I was very, very glad to discover coming here that a lot of people are working in this.
I mean, we are not.
Okay. Oh, well, the signature is spreading everywhere. No one knows where is the signature. Okay, so we have to definitively to come to Cambridge to discover a paper of our team, of the French teams. Okay, so if someone knows of my...
There is a second paper.
Okay.
The first paper
Okay. Okay, so thanks to Cambridge and thanks to Isaac Newton Institute, we discover that people that we know are writing papers about the signature method. And that's very nice to see that a lot of people are interested in this topic. What I am going to see, so I don't know how many time I have. I don't want what. Oh, okay, what I am going to speak about is to say that if we want to perform an ML task, there are several basic tools that we need to use. And the first basic tool is the mean. So there are two tools which are basically the mean and the PCA that we may want to extend, okay, to the signature space. And I think I will have time to speak about the mean. I don't know if I will have time to speak about PCA. Okay. So the point is that integrals seems to be very simple, but they are not, and they are not because, for example, you see that there are this relationship between order 2 and order 1. There are a lot of you are not basically you are not in a Euclidean space, and in fact you are not also in a Riemannian manifold. So if you want to describe this object, it is a complex object, in fact. So if you want to extend a basic object like mean PCA, it is not so simple because the signature space is something complex. But you want still to use it because from the computational point of view, you have nice properties. Okay, so so we also worked on anomaly detection. We'll skip this part. We provided a multi-scale version also. It could be, I think, related to the isolation forest. And okay, we can do really nice things. Okay, so I will now speak about the question of the mean because it is, I think, it is a central question. Okay, it is an important question in any statistical task. So I will just give you some few things. What time is it, please?
11:20. 20.
Okay, okay, I take a few minutes. Okay. Okay, so just to remind you that clustering is a very basic task, and anyway, to compute the mean of time series, it is something very useful. Okay, and the motivation is the following. In many cases, you want to average. Okay, it is a basic step, and the point is that there is many possibilities to average a set of time series. So you have a set of time series, you can just average, but for example, imagine that your time series have not the same length. So it is a practical difficulty. Imagine also that you have missing values, okay, in one time series and not in another one. So you have many situations where the naive average is not possible. It is not so simple. The idea of averaging as if we are in the Euclidean space, it doesn't work in practice for many reasons, also the curse of the dimensionality, and for many reasons. Okay, so people have done several things: Euclidean distance, D2W, and there is also papers about stationary time series. If you are considering the spectrum, after that you may use you have a PDF and you may use a Wasserstein distance. And what we try to do is to average time series in the signature node. Okay, and we claim that it is nice. It is a good idea, yes. But the point is that I think, for example, the non-stationary case, it could be interesting because the non-stationary case, it could be dealt with the signature method. Maybe it could be more difficult with other methods. And we have also this idea of dealing with time series of different lengths, which could be a burden. And the point is that if you average two signatures, it is not a signature. And for one reason, it is because you have nonlinear relationship. So if you average, for example, two signatures of order 1 and two signatures of order 2, there is no reason to have a Fibini-like formula, because you are truly nonlinear. So if you average in a naive way the signature, it won't work. Okay, and the point is that the signature is a Lie group. So we can dive in the paper of Pennec, Xavier Pennec, who wrote a lot of nice and beautiful papers about this Lie group setting. Okay, so I just claim that here, I just claim that if you want to think about the signature, you have to think to it as a formal series. Okay, and if you use this formal series, you can multiply it. It's like a polynomial, in fact. Okay, it is here you have something which is like x to the power k, and when you multiply, you recover exactly the formula that you will have for polynomials. And then you have, and it comes from a Fibini-like formula. So if you have an algebraic structure. Okay. And thereafter, since you have an algebraic structure, you have logarithm and you have exponential. And you can use the fact that it is a Lie group. Is the idea okay? Okay. So just I show you the different approaches. So first approach is you have a group, okay. You want to average different elements of the group. What you do, you go first in the tangent space, you average, and thereafter you come back to the group. Could be a first idea. Okay? And the point is that if you do that, this thing is not working. So what you want to do, in fact, you may have some paths, and you want to average this path. But what you want that this operation is invariant with respect to concatenation. Exactly.
Okay, so, but then, yeah. So the operations that you define, I mean, they are how they behave with respect.
Exactly. Exactly. You want that when you concatenate, and then you want that average plus concatenate is the same that concatenate plus average. And it is exactly the idea. And to have this, it is a group property, which is invariance with respect to the group product. And then you want to have this group property. And if you don't have that, it is not meaningful from the practical point of view. Yeah, exactly. And here, what you want, basically, what you are doing, you are considering the definition of Pennec, okay? And Pennec, what he's doing is considering the mean as a barycenter, okay? And if you do that, it will work because you will have an optimization function that you can penalize, and you can have also explicit formulas. Okay, so just to conclude, this is just to show you that, okay? So if we have a barycentric definition of the mean, we go in the tangent space and we have a barycentric definition, okay, of the mean, and thereafter we go back. Okay. And the point is that since we have a Lie group, there are some relationship between the different tangent spaces. Okay, okay, and we have this. It is exactly the definition, the barycentric definition. Okay, so just to conclude, okay, we prove that we have existence and uniqueness. We have our invariance properties, and we try to use, here it is an example of calculation. We can calculate it in a practical situation. And then, for example, we can use this as a preliminary step for clustering, for example. So here it is silly autoregressive model. And here we have, for example, this data set. Depending on the country and the state, we can clusterize the income data set. And here we find clusters that may be relevant to the East Coast, West Coast, and inside US.
So the way to gain
Exactly, yeah, exactly, yeah. In fact, the aim was not clustering, it was to define important tools using, that could pave the way for other situations. Okay, so thank you very much.
Thank you.
I can ask you, so you got these integrals, but you're estimating them from noisy data.
Yeah, true.
Did you think about the uncertainty in the signature objects?
The point is that, the first point is that if you have noisy data, since the signature is nonlinear, the noisiness won't be the same according to different order. In fact, we are too noisy for higher order. It means that at first, we have to consider low order of the signature. We cannot, after that, we are too noisy. And I think, we maybe, no, we have no idea about the uncertainty, but maybe it could be done, okay, because it is a Lie group and we have some information. So probably it is possible to do so. The point is that if we want, for example, to have a conformal interval and so on the signature space, we have to define it properly. And I am not aware about conformal definition on Lie group. So I'm missing something. I'm missing the basic concept to define it in a proper way. So maybe I have to understand more on this topic.
I mean, it might be a daft idea, but we know, for example, that the first ordinate rule you were doing, or the trapeze rule, or the posterior mean if you assume the underlying function is a Gaussian process for the particular kernel, and so you get uncertainty for free in a sense about the this is probabilistic numerics kind of literature.
Okay. What you would do is, for example, have a prior on the first order signature.
On X.
Yeah, true. Oh, yeah, true. That's a good idea. Yes.
I think you're doing
But maybe in an empirical way, because if we do that, I don't know if it is simple to do it in a theoretical way, maybe an empirical way, maybe it could be possible. But the main difficulty is we are in a Lie group, but maybe in an empirical way it could be possible. And there is also this fact that we have some correlation between the different orders of the signature. So it is also not simple to take that into account. Yeah, but yeah, it could be interesting. Yeah.
Can you interpret with the signature what differentiates the cluster in the slide before?
Here it is not the signature, okay? So in fact we did row clustering, in fact, calculating the signature, and we perform row clustering. So it is yes, and yes. So there is also another point. Okay, it is a signature is not so easy to visualize. It is the reason why we have these two bottlenecks. The bottleneck of PGA, okay, to project, for example, the signature on principal component to be able to visualize. And there is another also bottleneck, which is, for example, so it is, so maybe using PGA, we can try to see if there are clusters of signature. Okay, so it could be a first idea. It could be a first idea, It could work.
maybe just come back to my previous question because I think I didn't understand it. So I said let's assume that I take a simple time series coming from xk plus 1 is equal to r xk 1 minus xk.
Yeah.
And then would you be able to this is not change point detection, it's more of a bifurcation behavior.
Okay.
I want to see if you are able to catch the change in qualitative behavior if you change R. Do you think that the signatures would allow to do that or not? Just
in fact, what you have is that for low value of R, you have a stable behavior, for example, and thereafter you are unstable.
Yeah, or you may have like a periodic orbits where you may.
Yeah, but if you are unstable, maybe it could be seen in the magnitude of the signature. I'm not sure, but maybe in fact, if you are stable, maybe at some point.
Because here you have like two. You may have like two equilibrium points, 0 and 1.
Yeah.
And you may be flipping from 0 to 1.
Yeah.
So do you think that the signature will be able to catch the change in the qualitative behavior? But again, this is not change point detection. It's really change in the qualitative behavior. So sometimes you go to 0.
I understand. 1, I understand the point. I don't know how possible it is. What I would try to see, maybe it could be the same question than Arturo. Maybe what we can see, if considering, for example, R corresponding to different regime, maybe we can try to visualize using PGA. We can try to visualize if we see some clusters of signature. So maybe the good question is not change points, but we can try to visualize if to see to try to catch if there is some qualitative difference between the two sets of signature. It would be my first intuition.
Okay.
Yeah, but I think the situation is not so simple because what you want to see, it is a chaotic behavior.
Exactly.
And I don't know how the signature is behaving because you will have a very maybe it is the magnitude of the signature which is high because you flip. So in fact the slope are very high.
Yes.
And then if you have very high slope, here you have derivative inside. So maybe, but
makes sense.
I think
I got it.
Okay.
Yeah, just a bit. So, up to which order have you used? I mean, when considering multivariate time series analysis, okay, first was for causality.
Yes.
Kinetic function expression.
Yeah.
Okay? And what you want to refer is a causal regulatory graph.
Yeah.
Okay. And if you want to use this approach, you agree with me that you have to consider, I mean, in principle, you want to consider high order.
Yeah, but it is very difficult.
And there is a difficulty that you pointed out at the very beginning of the talk. Okay, so I would like to know, I mean, how much, I mean, do people use this for extract causal?
Yes, they do this. We can do it to extract causality, but the point is that it doesn't scale very much.
Yeah,
in fact, the problem is a scaling problem.
Yeah, so you absolutely. So you look at very small.
Yeah, for causality you can look at very small graphs, for example, up to 10 or up to 5. So because it doesn't scale because you will have large tensors. And an alternative solution, we are exploring this with a PhD student, with Michel Sebag, and we are trying to reduce the complexity of the problem using a divide and conquer approach. And the idea is to compute what is called the Markov blanket.
Okay.
And the Markov blanket is you have a node, and you want to see just who are the parents and the children of the node. And if you divide the graph in small pieces of graph, maybe you can do something if you have a smaller word assumption. That's not so simple. Thank you very much.
Thank you.
Thank you.